So today I'm going to present VerMI, a verification tool for mass tower implementation. So now we are trying to answer one of those questions that Lauren is missing. We're trying to provide these tools to evaluate our algorithms, our implementations. So why do we need these tools? These hardware protected implementations are quite complex, and we need very specific and dedicated labs to do this evaluation. We need a big team of experts with high qualifications to run those labs and to check that those verifications are made correctly. What else can these tools help us? They can help to provide a correct verification and to minimize human errors. They can help on the automation of this process, ultimately reducing the time to market of a certain product, let's say. So this is the outline of my presentation. I'll first talk about the highlights of our tool. Then we'll give a brief explanation of threshold implementations and how we evaluate the properties from threshold implementations with our tool. So let's start with VerMI. This is the framework of our tool. Our tool receives an RTL file with a VHDL or a Verilog architecture. It synthesizes, creating the netlist, and from the netlist builds a structural model with which then evaluates the properties of the sharing scheme known as threshold implementations, and then gives a security report of the scheme, of the implementation. So we implement the tool in C++. We use Synopsys DC compiler to perform the synthesis of the circuits. So the tool works at synthesis level. The conclusions that we can get from the tool, since it is a synthesis level, serves for both FPGA and ASIC implementations. The user needs small interactions with the tool. It needs to provide a small header to tell the tool which are the secret variables and which are the random variables that the tool needs to take into account when analyzing the properties. We use the basic circuit elements to build the structural model, parsing the netlist produced by, in this case, Synopsys. And then from the structural model, we start evaluating our properties. So, what is threshold implementations? Threshold implementations is a side channel analysis countermeasure. It provides probable security with minimal assumptions on the hardware. This means we have a theory behind our implementation to back up the security claims. And it also provides security in the presence of glitches, where unexpected dependencies might occur due to this behavior of the circuit. Threshold implementation is a Boolean masking scheme that is based on secret sharing and multi-party computation techniques. These are the properties the threshold implementations propose to make a design secure, namely correctness, non-completeness, and uniformity. I won't get into details of defining them, but I will show how the tool checks them. So, well, we don't check for correctness because that's only checking that the output is correct, so that's simpler doing it yourself than implementing it in the tool. So we start with non-completeness. From the structural model, we do a tree search from every output backwards to gather the input dependencies. So we build a tree, we get the input dependencies, and then we evaluate the non-completeness over all these outputs. We need, for non-completeness to succeed, we need that every output has to be independent of at least one input share. In this case, we see that P1 and P3 are fine because they don't depend on all inputs. but P2 depends on every input, so we could say it fails non-completeness. So now, how the tool does it for a bigger implementation, for a big implementation? Well, this is not a big implementation, but it's a small example to illustrate how to do that. So the tool builds a matrix with the sensitive data, with shares in the rows and different variables, with shares in columns and different variables in rows. And then, for every output, we define that same matrix. We build this same matrix with the dependencies. In this case, if we look at C1, for example, it depends on x1, x2, y1, y2, right? So then, once all these matrices are built, we check that every row is safely missing one of the input shares. Here, it's fine, but let's say we're implementing this small example and we mistake a wire somewhere here, somewhere there. So we end up with an implementation like this. We swap these two terms, okay? So now we build again the same matrices, and we see that dependencies have changed, obviously. These two are still fine, but C3, let's see, it depends on the three shares of x1. So here we would say that C3 fails non-completeness for the first variable. How we do that for higher orders? For higher orders, we follow the same procedure. We build a basic matrix with the sensitive data, and this time we build the matrices for combinations of outputs. So how do we define this order non-completeness? This order non-completeness is defined as all the possible combinations of output shares have to be missing one of the input shares. So we do that here. We take every combination of outputs. In this case, we analyze a second order security. So we take combinations of two outputs, C1, C2, blah, blah, blah. So in this case, all of them fail non-completeness since this is a first order security sign. But let's check what happens in a second order security sign. So we get an example of 6 input shares, 7 output shares. We build a sensitive data matrix, and now for every combination of 2 outputs, we have to build the same matrices. For the sake of brevity, we show just a couple of examples. So for example, if we combine C1, C2, we gather all the dependencies of this combination. We fill the matrix, and we see that both rows are missing one input share at least. So we say it's fine. We do the same with C2, C5, C4, C7, and we see that there is always at least one input share missing for both variables. So we say non-completeness for second order non-completeness is correctly fulfilled. This we use the same method for third order and so forth. So this was for only combinational logic. What happens if we add sequential logic to our circuits? We have a circuit like this. So first what we do, since registers for non-completeness, they only serve to synchronize the circuit. So what this does, it's thwarting the propagation of glitches farther on in the circuit. So what we do is check the non-completeness only locally for every sub-combinational circuit. So we divide the big circuit into small combinational circuits, and we evaluate the non-completeness on every of those circuits. So let's see how we do in an example. Let's take protected AES Sbox implementation and see how we do. So now we have more combinational circuits to analyze, so we need the user to give us more information about the secret data. So similarly as for the inputs, we give the user has to give the sensitive data for the inputs of every layer. So let's focus on the stage 3, for example. For this subcircuit, we will build the sensitive data matrix as we did in the previous examples. So here we see the top variables. We have 4 variables in 2 shares for this top wire. For this bottom wire, we have again 2 shares, 4 variables. And for the wire in the center, we have 4 variables in 4 shares. So the tool knows how this combination works, and it will look at every row to see if it is filled or not. So with this analysis, we were able to find a flaw in the literature, a non-completeness flaw, in a round-based implementation of COSIC. And we also had the authors recognizing in their ePrint version our findings. Then, how we analyze uniformity with our tool. Uniformity, we'll continue with the same example, and we explain how we analyze uniformity here. So, for every different unshared inputs, we give every possible sharing, we compute every possible sharing of these inputs, and we check the frequency of occurrence of the outputs. If they are different, we say it's not uniform. If they are all equal, we say it's uniform. So in this case, this example is not complete, but it's not uniform. So to evaluate the uniformity, we simulate. We use our structural model to simulate. For doing that simulation, we use event-driven simulation. And how do we do with flip-flops now, with registers? Given a circuit like this, like the previous example, we change those registers into buffers, because for analyzing for uniformity, registers don't affect on its behavior. So we simply change the registers into buffers, and we evaluate the circuit from inputs to the outputs directly. This allows us to save the implementation of a scheduler or a clock cycle or something like this. We evaluate 3 different examples of the literature of a COSIC Sbox implementation. The first one from the authors using 3 shares. The second one from Leuven et al. Using 4 shares. And the third one, changing off the guard from Jamdan using 3 shares and 2 bits of randomness. And we see, as expected from the literature, that the first version is not uniform because we see different frequencies of occurrence along the different test vectors. And for the second, the 2 other implementations, we see that they are nicely uniform with only 1 frequency occurring. So in this work, we've presented a practical verification tool for masked implementations at synthesis level. This is a necessary condition since we only work at synthesis level and still many things can go wrong, like coupling, for example, when placing or deploying a design. We provide so far only univariate assessments, and with the tool we could spot a flaw in an implementation from the literature. So what's for the future, and also something that we've done already. So we've implemented already fault detection in our tool, and we name it VerMI, verification tool for fault injections. Still to do, we have to implement a multivariate analysis, so across different cycles, and yet again a bit more to do a combined analysis on the implementations. So that's all. Thank you for your attention.